Hello, student. Today we are going to learn. Recall that in my last lecture we discussed about weak law of large number. Okay, so which tells you that average value of IIT random variables that converts to the mean of the distribution. So this is in probability, the conversion and distribution probability. And today we will learn something called the strong law of large numbers. Okay, and this is probably one of the very important theorem in probability theory, and there are lots of applications in especially in stochastic processes. When we will start learning, we'll give some example from there, and also in there are lots of examples, so I will try to tell what are those things. Okay, so what do you mean by strong law of large number? So generally these kind of things appear in sampling theory when you do um, sampling. For example, to predict, so suppose you have a population and you want to this is the your population, and you want to predict some property of the population, and then uh, so it is not possible for you to collect the property for each of the member of the population, so you collect some of the members from here and there and try to observe their property there. So these are called sample. Okay, and then you predict about their property. So these sample values, these you can think these are the values of some random variable. So yeah, so what? So so these are what this collecting of these properties are kind of random experiment. Okay, so these are kind of random experiment. And you are repeating some random experiment, and the results are the outcomes of random experiments, which are kind of, you can think, values of random variables. And because the same experiment you are doing, so these are IITs, so identity distributed, but they're independently you are doing the random experiment. Okay, so in these kind of cases, the strong law of large number actually appear, and it has lots of applications. So let me write down the statement first. Statement. So the statement says, so let x1, x2, and you have this sequence be a sequence of IID random variables. Okay, so identically and independently distributed random variables with say this is finite, say I mean obviously, maybe this is finite, this, and also I'm assuming the fourth moment is finite. Okay, yeah, so the proof you can use the proof without that property, fourth moment is finite, but the proof will be more lengthy, so we use this property. But yeah, so the theorem is true without this property also. Then what happened? Then this average of this random variable, average of these that converts to mu. Mu is the um, mean of the distribution almost surely. Almost surely. So what is the meaning of almost surely? So that is, so let me write down mathematically. This means that probability that limit n tends to infinity x1 plus x2 xn by n equal to mu. This event, the limit of this event probability will be having 1. So this is full probability. Okay, so that is called almost surely. Okay, and so you can understand that there is a difference between strong. So note that. So the main question one can ask, then what is the difference between the strong law of large number and the weak law of large number? Now recall what is the weak law of large number? So the weak law of large number uh, uh, implies, what does implies? And that for any some large value, any large n, so let me write down my Sn is sum over xi, it will reduce. So this Sn by n, which is this, um, is tends to mu. Okay, so this is in probability. So in probability. So what does that mean? That means um, uh, okay. So yes. So in probability. So um, so what does that mean? That means so you cannot say that this quantity. So now you choose any some index which is larger than n, then you cannot say what about index by index, whether it is this tends to, this is this is yeah, so this tends to mu or not. So I mean to say that, so if you have some another natural number, large number which is bigger than that, so you cannot say that this quantity is index by index is also very close to mu or not. But the strong law, but the strong law of large numbers um, uh, say large number implies that with probability 1 with probability 1 and for any epsilon positive, this quantity uh, Okay, so so the quantity that uh, rather I should say xi over n I equal to 1 to n minus mu. So this quantity um, um, cannot be this cannot be larger than epsilon infinity. So this, so or rather we can say this will be uh, greater than epsilon only for final limit cases, only for a finitely finitely rather finite number of times, yeah, finite number of uh, n's. So if you choose, if you replace your n's by another larger n's, so this quantity is actually very close to mu. So this quantity is very close to zero. So more of this quantity close to zero. So that not larger than epsilon. It can be larger than epsilon, maybe in rather I should not say finitely many times, but with um, so wherever this quantity is larger than epsilon, so that's it as a measure zero. Rather, I should say measure zero. Okay, so but we did not learn. So this is a undergraduate course, first course. So we did not learn what is measure theory. So you can think only finitely many times. Okay. All right. Yeah. So so now the the proof is actually very much intrinsic. So there are proof interesting, obviously, but so we will the proof. We will try to give you first a proof without using something called Borel-Cantelli lemma, and there are I mean obviously there are many proofs, so I will try to give two basic ideas of the proof. Okay, so let me start with the proof. So um, so maybe we can assume, so we assume first that mu equal to 0. So start with that mean 0, and then what you can do, then we have a lemma. So you can prove this lemma. So it tells you that so your Sn is summation of this partial sums I equal to 1 to n, and so lemma tells you that expectation of this Sn, fourth moment of Sn by n power 4, this is bounded by some constant time over say n square. Okay, and this is we are going to prove first. We're going to prove that expected values of this is bounded by some constant time 1 by n square, and that will give you the convergence part, and then we will prove the theorem. So how to prove? So proof of the lemma. So proof of the lemma. Okay, so we start with this quantity, expectation of Sn4. Okay, so what does that mean? That means you're taking kind of x1 plus xn, and then you're multiplying by again x1 plus xn, and so on again, x1 plus xn 1 2 3, and the last one is also x1 plus xn. Okay, so SNs are sum of x1 x1 to xn, so you are multiplying 4 times, and then when you multiply these terms, you will see that inside, after multiplication, there will be term like uh, xi 4, and I can be 1 to n. Similarly, this fourth term, then there will be 3 multiplication with one single term, and then there will be term like twice, so xi square xj square, and there will be term like xi square and then xj into xk. So these are ijk are different, so ijk are different number in between 1 to n, and similarly there will be all distinct product xi xj xk xl, like this kind of term will be there. Now you now look at these terms. Okay, so 1 2 3, this type of terms. Okay, there will be many such terms. So like so one such example can be, you can say x1 cube into x5. Okay, similarly x1 cube into x7, something like that, or x2 cube into x7, like this kind of term. Okay, now note that whatever these terms, for example, if you have um, expectation of xi cube into xj, then what happens? Then we know that these xi xj are independent. Okay, so what does that mean? That means xj is also independent of the xi cube, because xj is independent of xi's, and then we know that in this case it will be nothing but product of xi cube into xj, right? But we already assume that the expectation is 0, right? Mu is 0, so this part will be 0. Similarly for uh, mm, xi square xj xk is also 0, and similarly expectation of xi xj xk xl, these are all 0. Okay, these are 0 because these are product of individual expectation, and which are 0, right? Now what are the surviving terms? So the only term which survive are expectation of, so term of this form xi to the power 4 and expectation of um, xi square and xj square, right? Now the question is that how many such term can be occur? Okay, so how many such term can be occur? For each I equal to 1 to n, there will be one xi power 4, right? So x1 power 4, x2 power 4, xn power 4. So there will be n many such terms for this first thing. So you can write down your expectation of Sn power 4 is n times expectation of xi power 4, right? Plus the number of terms of the form of this form xi square xj square, right? But you see that obviously see for any pair fixed I and j, so how many ways you can have xi square by 4? So this will be 4 choose 2 many ways. So 4, what is 4 choose 2? 4 choose 2 is nothing but 4 into 3 by 2, so 6. And you can have obviously you can choose ij also of the form in choose too many ways. So in choose 2 means n into n minus 1 by 2. Okay, so total number of options will be what? Will be 6 into n into n minus 1 by 2 into expectation of xi square xj square, right? And hence this will be nothing but n time expectation of xi power 4 plus 3 into n minus 1 into so again we will use the independentness property here xi and xj, so you can write down xi square, okay, into expectation of xj square, right? But we know that these are expectation of xi, expectation of xj, these are same whatever the expectation, because they are IIDs, and hence finally you can write down n times expectation of so I am writing this expectation of x power 4 because these IIDs, so all are same, okay. So x power 4 and here 3 into n minus 1 times expectation of x square and then whole square, right, twice, okay. Now we already know the estimate for these terms, and we need to have estimate for these terms, okay. Now how do we estimate? So again you notice that so the variance of x square is nothing but expectation of x power 4 minus expectation of x square whole square, right? And variance is always non-negative, so this is equal to 0, and that gives you the bounds that expectation of x square whole square, this is bounded by expectation of x power 4, okay. Now if I assume that this quantity expectation of x power 4 is some finite number, what I already tell in the beginning, say something, say k, then what happened then, so this is my number one equation. Now the number one equation becomes what? So that will becomes expectation of Sn power 4 is bounded by n then k, so n into k plus 3 into n minus 1 into k, right? Yeah. Okay, so now you see that dominating term is n square. So you can say that this is bounded. So in number theory we write down n less than k n square. So what does that mean? That means so this means that expectation of Sn power then is less than equal to some constant time n square. Okay. Because this is n square is the dominating term here. Okay. For large n, so for large n, okay, and hence so this gives you the lemma that Sn power 4 by n power 4, if we divide 1 by n power 4 is a constant, so this will be some constant, yeah. So and this c is some positive constant, okay, k is positive, so this is positive, it cannot be negative because this is expectation x power 4, right, the fourth moment, so it's positive, okay. So this is bounded by a constant time n square, right? So this is one important identity which already this is the main important part of the lemma. And now using that lemma, so how to prove this thing? So so what is this quantity expectation of summation? You see Sn power 4 by n power 4, and then you have n equal to 1 to infinity. So this quantity is what? This quantity is nothing but, you can write down, you can take expectation inside, so n equal to 1 to infinity, and then expectation of Sn power 4 by n power 4, which is bounded by c over n square, so this is less than equal to constant time summation n equal to 1 to infinity 1 by n square, right? And you know that this quantity is finite. This quantity is finite. This quantity actually is nothing but zeta 2. Yeah. So or rather I should say y square y6 is quantity summation 1 by n square. Sorry. Um, yeah, so 1 square, 2 square, 3 square, yeah. Yes, so this is whatever, this is finite. So what does that mean? That means expectation of this series is finite, okay, and hence the series itself is convergent. So this implies the series is convergent series. Xn power 4 by n power 4 n equal to 1 to infinity. The series is convergent series, right? So this is convergent series. Okay, this is convergent series, and by the property of convergent series, if the series convergent, then the nth term goes to 0, and hence the nth term of the series, which is nothing but Sn power 4 by n power 4 tends to 0, and this implies Sn by n tends to 0, okay, with obviously so this is with probability with probability 1, because um, if this is not finite with some probability infinite, then the expected value will be infinite, where we saw the expected value is finite, right? So with probability 1, this is this quantity is finite, and hence Sn over n uh, tends to 0 with probability 1, or what is we saw almost surely, okay, and done. So this is the proof. So obviously 10, when I am saying converging, I mean as n tends to infinity, okay, so as n tends to infinity. Okay, so so this is the essential proof. So summation Sn over n converts to mu, here mu equal to 0, right? Now in general, so in general, if say mu not equal to 0, then what happens? Then you rename your xi as this yi by xi minus mu. Now you see that expectation of these yi's are all 0, and then you can apply your PBS theorems, and then if you apply for then you will have what limit n tends to infinity and summation yi over n I equal to 1 to n is equal to 0, because yi has mean 0, but this means limit n tends to infinity xi is minus mu over n I equal to 1 to n equal to 0, and hence limit n tends to infinity this xi by n I equal to 1 to n equal to mu, okay, with probability 1. So this is mu almost surely. Okay, so so this is one proof, but yeah, so but you can have a almost similar but little different proof involving something called Borel-Cantelli lemma. So let me discuss that. So what is this something called Borel-Cantelli lemma, or rather so I will, so there are two versions, so I will talk about the first person, Borel-Cantelli lemma, this first person, okay. um, I mean you have one more person, so but we will have this. So this tells you that let You have say E1, E2. So these are the sequence of events, and E V the event. If a special event, what is that? E is nothing but event that so out of these EIs, when you do a random experiment, infinitely many of them occur. So what is that? That infinitely many of them occur. Okay. So what is that mathematically? So that is, so what do you mean by infinitely many of them occur? So mathematically it means that E is the lim sup limit to infinity supremum of this En, which is also you can write down in set theory notion. It's saying that the intersection of n greater than equal to 1 and then union over k greater than equal to n ek. Okay, so you take first n equal to 1 and then take union of e1 e2 dot dot everything, and then for n equal to 2 yeah, so this is union of e1 e2 and everything, and then when k equal to 2 you'll have union from e2 3 k everything. So and then after taking union you take the intersections, and that is the this here, which is nothing but infinitely of them occurs. Okay, so that is in the intersection of all those unions. Okay, so yeah, under all those things, so the statement tells the parent content says that then uh, probability, then summation probability of n equal to 1 to infinity is finite, implies, it is finite, that implies that probability of E equal to 0. Okay, so what does that mean? That means if this sum is finite, convergent, then probability that independently of them occur is 0. Okay, so this is very interesting, right? It has lots of applications, so I will show you one application to prove the strong law of large number. Okay, so how to prove this Borel-Cantelli? So let us try to prove. So what is the ODE? So now you see that E is what? E is intersections over n greater than equal to 1 with union k greater than equal to n and then ek, right? So intersection of these events, right? So what does that mean? So if something intersection of many events, so it is inside those events. So what does that mean? That means E is inside union of k greater than equal to n ek for all n greater than equal to 1, right? For every n. Clear? Now if you know that if A intersect A subset of B, then probability of A is less than or equal to probability of B, and then similarly you can have probability of E, which is less than or equal to probability of K less than or equal to N K, right? But this probability is obviously nothing but union of En for all the n's, right? Instead of taking this, so it is for everything, and we know that, remember Boole's inequality, So last inequality is bounded by sum over probability of n equal to 1 to infinity. Okay, but in our assumption we assume that this probability is finite, so this sum is finite, so this is finite. Okay, or rather this converges, so this converges. Okay, okay, so this converges. Okay, now if the series converges, then the tail tends to 0. You know that, right? So you have learned this thing series. So the tail of the series uh, goes to 0, right? If the series converges. So what does that mean? What is the tail? Tail is nothing but k greater than equal to n expectation. And this is the tail of the series, right? So that goes to 0, right? And hence you get probability of E, which is bounded by sum over probability of E k greater than equal to n, which is goes to 0. So k as n tends to infinity. Okay. Okay, and this implies this quantity is 0. The probability is always greater than 0. Okay, greater than equal to 0. And this right hand side goes to 0. So this probability of all infinitely many of them occur is 0. Okay, so this is the proof of Borel-Cantelli lemma. This is the first version, and we can use this first version to prove strong law of large numbers. So another proof of strong law of large number using Borel-Cantelli. Okay, so proof. So how do you prove? So you have so you remember we prove there the expectation of um, Sn power 4 over Sn power 4. So this quantity is some bounded by constant time n square, right? So and this is even true if you replace. So that was the case when the mean expected value is 0, but expected value is not 0, then the corresponding theorem will be what? The expectation of. Okay, so we can write down by this Sn minus n by mu to the power 4. Okay, so mu equal to 0, that is nothing but exactly this. This has the same bound. Okay, and proof is similar. Okay, so this is the bound which already proved in the first case, the first proof, and this bound is going to help me, right? Now, yeah. So now how do we prove? So the proof start like that. So we have, for example, I would like to know whether mod of is n over n minus mu this quantity. So I would like to know whether it is large or small. My goal is to prove that this is tends to 0, right? We want to know this what is the probability of that this quantity is larger than some n power gamma, some gamma positive. What is this probability for some gamma positive? Okay, and we know that this is bounded by, okay, so let me write down this quantity as again Sn by n minus mu to the power 4 bound greater than equal to n power 4 gamma. They are same, right? And this quantity is bounded by you know the expectation of so I will write down. So this is expectation of Sn minus n, Sn by n minus mu power 4, okay, and divided by yeah, so divided by n power minus 4 gamma. So I hope you remember this is from Markov inequality, Markov inequality, okay. And we just and then look at the numerator. Numerator we already have bound, so numerator is bounded by this quantity for some constant c. So this is bounded by c times into the power 2 minus 4 of gamma, okay, some c positive, okay, clear. So so this quantity, you know, have a nice bound, and now you will define this with the help of this. We will define these events. So what are the events? So so my events ENs are okay. So one more thing. So I need to use Borel-Cantelli lemma. Okay. So let me write down the events. So this is first model Sn n minus mu greater than equal to m power minus gamma. This is my events, and I would like to check whether the sum of probability of ENs n equal to 1 to infinity, this is finite or not. This is what I'm going to check, right? But what is this? So this is nothing but probability of this quantity. You already know this is a bound. This bound is c over this. So this is bounded by this is less than equal to. So okay. So this quantity is less than equal to sum over c times n over 2 minus 4 gamma n equal to 1 to infinity, which is nothing but c, okay, c over 1 by n power 4 gamma. And we know that these kind of series converges if so this the series will converge if this 2 minus 4 gamma is bigger than 1, right? So what does that mean? That means so 4 gamma is less than 1, so gamma is less than 1 by 4. Yeah, so what does that mean? That means gamma is in between 0 to 1 by 4. Gamma is positive, we already assumed that. Okay, clear. So if I choose my gamma is in between 0 to 1 by 4, then this series converges, right? Okay, so then what does that mean? Then for gamma in between 0 1 by 4, sum over p of n equal to 1 to infinity, this converges, and that implies probability of e equal to 0 using Borel-Cantelli lemma. Okay, and this implies probability that E complement is 1. Now what is E complement? So now I try to understand a little bit. So E is what? So E was intersection over n equal to 1 to infinity, n greater than equal to 1, union over say m greater than equal to n, EM, right? So this was your E, and then E complement will be nothing but uh, full complement, which is nothing but so these are your kind of intersection of some events. So this will be union of those events, right? So union n greater than equal to 1, then those events, De Morgan's law. Okay. Now again inside this is the union of some events is nothing but n greater than equal to 1. So this you can write down as intersection of m greater than equal to n em complement. Right. Now what are EMs? Um, EMs are this. Okay. So what is the complement of this set? So this mod value is less than n power gamma, right? So what does that mean? That means this tells you that uh, so this is if and only if, okay, and this is also if and only if. So if and only if to the probability of E complement equal to 1, so this is if and only if or if and only if, okay. And so what does that mean? This last event, means that uh, mod of Sn by n minus mu is bounded by n power gamma, okay. uh, okay, so um, for all n greater than equal to some n, so there is, I should write down, there is a capital N belongs to natural number such that this quantity is bounded by that, okay. And so now it is clear that um, this means that limit of Sn over n tends to infinity equal to mu, okay. This means this is equivalent to this, and this quantity is equivalent to probability that E complement equal to 1, right? Clear? So this limit will be mu with probability 1, okay. So this is another proof of um, strong law of large number, okay. It has lots of applications actually. So in fact most of the applications you can find out in stochastic processes. When you learn stochastic process, we will give some of the example. Now let me give another example here. So without going to the Markov process or other Bernoulli process, I mean without telling those things. So let me tell you, for example, suppose you have a say so you are performing some random experiment, okay, and let E be a something, say fixed event of a random experiment, and what is P? So probability of E is in the probability that E occurs on any particular trials, okay. So you are doing a random experiment repeatedly, so you have trials, and then we define another random variable, define say xi, which is either 1 or 0, so one only random variable if e occurs on the ith trial and 0 if e does not occur in the ith trial. Okay, so this is a Bernoulli random variable. You can say that you take value 1 and 0, right? And then what is that strong law of large number tells you? So strong law, so what is first of all expectation of this exercise? So this will be 1 times probability that this is 1 time that probability that x equal to 1 plus 0 times probability that x equal to 0, but this is what? This is nothing but a probability of e, so this is this and this one is 0, so it doesn't matter, so this is probability of e, right? And then so this is one observation, and then the strong law of large number, strong law of large number, what does it say? So large number tells you that number implies that with probability 1 with probability 1 this x1 plus xn over n, that goes to that the mean, which is nothing but expectation of x, or rather xi, whatever they are, same IITs, right? This is nothing but PE. Okay, so what does that mean? So so this means, so let me explain more. So you see that what is x1 plus, so your Sn is what? Xn is what? So this is this represents and the number of times that the event E occurs in the first n trials, right? So I'm doing first n trials in trials. Okay, so from these equations, summation this tends to PE. So that means what? That means that the limiting proportion of time of the event E occurs is just so what is the implication? So thus what's strong law of large numbers tells what? That with probability 1 the limiting proportion of time that the event E occur is nothing but probability of E. Okay, so if you have average of this and then find out the limit of the average. It is nothing but the probability of this E. So, and these are obviously going to help you in stochastic process to understand more. Okay, so by this I will stop today's lecture, but I would like to tell you that in last quiz, in the problem involving Mountain function, maximum people have not done correctly. Okay, so for example, okay, so solution Q is 3 or 4. So Mountain function was e power, let's say, t squared by 2, and then people take derivative, first one derivative and two derivative, and then they said, okay, then finally we have this from our observation. So observation does not give the proof. Okay, so either you need to find out the any derivative here, okay, for n equal to 2k and 2k minus 1, even or not, or you can use your series expansion. You know that this is nothing but um, so you know that e power x is nothing but this, so t square by 2 whole to the power I by factorial I equal to 0 to infinity, and then you can expand it. So when you expand it, then it will become t power 2i by 2i to the power I into I factorial I equal to 0 to infinity. And then you see that in this series there is no odd term of t, right? And you know that this is nothing but expectation of x power I is that I expectation. So okay, so there is no odd term, so 2i and then t power 2i by 2i by I factorial, right? I factorial. Now you can compare. So if you compare that, then x power 2i minus 1, the odd term will be 0, and then even term will be. So the problem was so simple. Okay, so even term will be okay. So am I missing something? Okay, yes, 2 power I I factorial. Yeah, so no, this is I, and okay, I must write down this properly. Okay, so I should say that in this is n equal to 1 to infinity expectation of xi power n into t power n by factorial n, right? Now when n equal to 2i minus 1 or there is no term, so it's 0. When n equal to 2i, so this will be n factorial by 2 power I into I factorial. So this is the proof actually. Okay, or you can, so this is one of the proof, or you can find out the nth derivative when n equal to 2i and 2i minus 1. But some of the student has they proved that for one or two terms, and then they said that similarly, or the trend or observe by observing, that is not the proof. Okay, yeah, I'll stop here.